All right, welcome back, everybody. So let's continue and move on to the next unit, to the next lecture of the course called Distributed File Systems. Before that, I just want to make sure to answer any questions, if there are any, from cloud storage, object storage, anything that is unclear. On Zoom? No questions either? Okay. So if anything is unclear, you have the textbook, right, of the lecture. So I encourage you to read this, and you can always come back to us for any questions that you might have. Also, you will notice, that there is a pattern in the course with a lot of concepts that are common across several weeks, and it's very likely that if some of the concepts we've seen in the cloud storage lecture are unclear, it might be that they will become clearer in the next few weeks, because we will repeatedly look at the same things all over and all over again, right? So lots of repetition. Okay, so now I have to explain to you what I meant with blocks. This is why you have these, right here, because I told you that in Azure Blob Storage there are blocks. So now I need to explain all of that. So far, we have covered relational databases, right? We have scaled out. If you correctly remember, scaling out is the second thing you should try after improving the code, right? Trying to write better code and squeezing more data in less space. Then you scale out. And then you can also scale up with bigger machines, but scaling out is usually the way that you can scale. I have to still mention that there are always trends, right? So sometimes it goes in a direction, then it goes in the opposite direction. I increasingly see projects and people that now start using less machines in the cloud with more memory and more cores. And this has to do with the fact that the computers, they are getting more and more and more cores. So this is a pattern that I do notice, that somehow the scale up tends to be a bit gaining ground again these days, right? But you never know what it's going to be in 10 or 20 years, right? So just so you know that there is a bit of a tendency these days that scale up is making a comeback, but you know that scale up is limited because you cannot scale up at will, right? You know that there is a limit to how many cores and how much memory you can have in a machine. Then we saw that for the purpose of cloud storage, or at least in the case of object store like S3, we have a key value model where you have bucket IDs and object IDs that are associated with the content of the object, which can be a web page, which can be XML, CSV, the content of a data set. It can be images, can be videos, whatever. So we have this super flat model called the key value model. The key value model, we'll probably see it every week. This is just, it's almost a mathematical or formal aspect. This is also called the map. It's basically almost a function, right? But it's a map. The difference between the two, map would also be a partial function, is that unlike a function, it doesn't associate to every theoretically possible key an object, but to some keys, to the keys that have been created. But anyway, this key value model, we'll see it at plenty of places throughout the lecture. Okay. Before we start with HDFS, I also wanted to comment a little bit on what we store at all these places in S3, in blob storage, in HDFS, and so on. It's like, the production with raw materials that you make things. Then there is the secondary sector that transforms them, and so on. It's a little bit the same thing with data, is that you have sort of the primary data. So this is what you directly get from your sensors or from your logs. This is the actual raw data that comes from the world. And then you query it and transform it, and you output new data derived from the raw data. This is called intermediate data also. So it's not the original data that you got from the world, but it's just something that you processed and then stored back to cloud storage or to HDFS. So it's always good to keep in mind whenever you look at data, is it the raw data that was collected from the real world, or is it some derived data that other people produced out of raw data? right? Then you can take derived data and again, compute derived data and so on and so on. This is more challenging than it seems because with so many people querying data and producing data sets, it can quickly become hard to keep track of where the data comes from, right? This is called data provenance, and this is actually a very trendy research topic as well, right? But just so you know that these systems like cloud storage and HDFS is not only to read data, but also to write data to, and then later we might read that data that we've just written. Okay. Now, let's come back to the introduction of HDFS. There is big data and big data. The key part to understand is that what we've seen in the context of S3 and Azure Blob Storage is a large number of huge files. Huge being larger than large. This is how I use huge and large, right? So I'm saying a huge, did I say a large number of huge files or huge number of large files? So I want to say for S3, a huge number of large files, right? Why only large? Well, because I told you it's limited to 5 terabytes. So 5 terabytes is large, fits on your laptop, it's not huge, right? Petabytes would be huge. Terabytes, that's just large. But huge number, because in S3, it's a worldwide service. People from all over the world that are storing their objects on S3, and it is one single service, right, for the whole world. So this is why we had a huge amount of large files, billions, if not trillions, of objects stored in S3 worldwide, right? So a huge amount of large files. But what about people who want to store a large amount of huge files? They maybe not want trillions of files, maybe just 1 million or so, but they want their files to break this 5 terabyte barrier. How do we do that? How can we store files that are too large to fit on a laptop or a single machine, a single hard drive? How do we do that? Well, you might have guessed it has to do with blocks, but it's something we will come back to, right? So just to make it concrete, object storage, billions or trillions of terabyte files. In file storage, you can have millions of files that can even go to the petabyte range. Of course, as we will see, just because you can doesn't mean you will, right? Doesn't mean that everybody is actually storing petabyte files, but theoretically you can. Okay. Now I'm just repeating the same thing multiple times, basically. But if you have this approach with billions of terabyte files, then this is the key value model with bucket ID, object ID, and then the content of the bucket ID, object ID, and then the content of the object. And this is called object storage versus what we will now do. Millions of files that can be up to petabytes. This will be a file system. So now it will not be fake. So these whole slashes that we will see will actually exist. These are real directories and real files, unlike what is simulated over there. And it's called block storage because the blocks are actually an important part of the system. And the blocks are the secrets of how we manage to go to petabytes. The first system that was created actually by a company, not academia. It was created by Google. So this is because it's these big companies that had these issues of scaling, right? They didn't have enough of the existing technologies because they had too much data to deal with. So they have to come up with new things. And Google came up with the Google file system, Google FS, in the early 2000s. So that's already probably 20 years old now. This system, but that's where it was invented. And if you look at what they wanted to achieve with Google FS, the first insight that you need is that if you just look at your laptop, it might fail. Who already had a full drive crash, like the laptop failed and they almost lost data? Nobody? That never happened to any of you? Some of you, okay. Who has a backup? Okay, very good. You know, on March 31st is World Backup Day. So if you don't have a backup, you can make a backup on that day. But basically, not everybody, right? So what I want to say is that crashes might happen, but they will not happen to everybody or not all the time, right? So it's basically a possibility that you need to consider and be ready for if you lose your data. But if you go to a data center that has tens of thousands of nodes, tens of thousands of computers piled up in these racks. It's not that it might fail, it's that it will fail. And in fact, there are people who have a full-time job in the data center who spend their entire days running after computers to replace defect parts. right? It's their job, and they do that the whole day. Because this just happens all the time. If you have so many machines, it's guaranteed to happen. So when you look at that scale of data and you want to store it in a data center, you basically need to build a system that works even though the drives keep crashing all the time. And the system must still work, and you should not lose data. So this is a requirement of a distributed file system to be resilient to this. So the way it works is that you have some layers in place. First, you need to monitor, because if a hard drive crashes, you want to know that it actually crashed. So you monitor them, then you detect that there is an error. Then you need to make sure that the system recovers or doesn't stop working just because the hard drive crashed, how we will see shortly. And that makes you fault tolerant, right? This is how the system continues to work. This has to do with the CAP theorem, right? This whole thing, the fact that you want to continue to be available as things actually crash. Even though when the hard drives crash, technically this is not a partition, right? So a network partition is really that you split your computers into disconnected parts. Here it's really just individual drives that keep crashing. Okay, so this is the whole idea. Another thing to look at in order to understand how a distributed file system in a data center is different from the file system you have here on your laptop is in terms of what you can do with the files. On your laptop, you can read and write files, but you also have some cool thing that's called random access. It means that your computer is able to modify or read a file anywhere in the file. Even if you have a gigabyte file, your laptop is able to look at just right in the middle of the file, or to even modify a few bits in there. This is called random access, right? What's the opposite of random access? So what would be a system like if it doesn't support random access, like you cannot actually read and write anywhere? Well, that would be scanning a file. What does it mean to scan a file? You open it, you look at the beginning, and then you read through the file all the way to the end. That's called scanning a file. This is not the same as random access. Random access is you open the file and then look at random places in there, right? Both for reading and writing. In the case of the Google file system and HDFS that we will see, this is all optimized for scanning files. Why does it make sense? Well, because we want to do data analytics. We want to store petabytes of data, and we want to scan through that data as quick as possible in order to aggregate the data, to learn things from the data. So when you do data analytics, you don't care about random access. You don't care. You just want to scan files, entire files, petabytes of files, as fast as possible. So the whole system is designed for that, while your small laptop is designed for random access. Okay. In fact, whenever you open, I don't know, files to edit, like in a spreadsheet or text processor or whatever, you might not be aware, but this is using random access. The computer is just replacing here and there randomly in the file some parts. Okay. For me, is that clear? This idea that scanning is very important, that we don't need random access for data analytics. Okay. Maybe it will become even clearer when we then cover Spark, MapReduce, and so on, right? So just put it in a corner of your mind that we are going to scan whole files and not going to do random access. Another aspect that we have is that we also don't have random access for writing to files. When we write to files, either we'll create new files or overwrite the whole file, or we are going to append at the end of the file, like a log. You just keep logging things. So we don't want to have a system, we don't need a system that allows us to write anywhere in there, right? At least not for the purpose of HDFS. So to summarize, we want to scan files, and when we write down data, we just want to create new files, overwrite files, full files, or append data to existing files, but we do not care about reading or writing random access. Okay. The append model, just to justify why this is actually useful, is just think where the data comes from. If it's raw data, it's going to come from sensors, right? For example, at CERN, when they collide particles, they have sensors that records all the data that is obtained from the collisions, right? So when you have sensors, this is linear in time, right? Time passes, and then every couple of seconds, you have new data that you append to your file as your experiment is ongoing. So this is why it makes sense. If you have the weather forecast, like Meteo Schweiz, they log the temperatures and the pressure and so on and so on. These are logs. They append things. They don't need to have write access to the past, right? The past is just recorded. It's not going to change, right? The temperature that you got yesterday at 2 p.m. is already recorded. There's no way to change that, right? So you keep appending as time elapses new data. The same for intermediate data, because as we will see, when you execute an Apache Spark job or a MapReduce job and you create the output data, this is also done by writing files in a linear fashion, just appending. But this we'll cover in a few weeks. Okay. And here, so I keep adding the requirements of the Google file system. We also want one more thing. When you're on your laptop, you're the only user of your laptop. So it's optimized for one person at a time. If you have a distributed file system, you might have hundreds or even thousands of people using it at the same time. It's huge. There's so many directories, you have so many users, they just use it at the same time. So you have some requirements there. And in particular, typically the requirement is that whenever you do something, you write something, you append something, it's atomic. What does it mean? So I kind of told you already, but atomic means that if you have two people accessing the same file at the same time, only one of them can actually write. You cannot have two people entangling their writes at the same time. That doesn't exist. The system must prevent that. So if you have sensors, like imagine you have 4 temperature sensors somewhere and they all append, it's in turns. One of them happens, then it's done, then the next one happens, then it's done, but they don't do it all at the same time. This is called atomicity. Okay. And the next requirement, this is also something that will all add up and become clear as we go through the course. Let me put it in a maybe intuitive and coarse way. What we want to happen in the data center when we use HDFS, we want bits to flow around. This is what we want. Data has to flow through the data center, as much of it as possible, as quickly as possible. Right? We are scanning files. We want to scan files as fast as possible. So we want bits to flow over the networks, as many of them as possible. So that means that the bottleneck of the system must be the throughput. It's like the network bandwidth, the speed at which you read on disks, doesn't matter. It must be the throughput. We don't want to be blocked by latency. What would it be? Just as a thought experiment, what would a data center look like if the problem has to do with the latency? We say that it's bound by the latency. It means that barely anything is ever flowing over the network. The system keeps waiting and waiting and waiting for things to happen. This is what latency is, right? Latency means that you're waiting for something. You're waiting to receive the first bits. So it means that nothing is flowing, right? But we want bits to flow. So this is why the system has to be designed for throughput. Flow. We want data to flow all over the networks and the electric cables, right? All right, and we'll see, of course, concretely that will also become clearer when I tell you what that means in reality for the design of the system. Okay, and that's actually directly related. So now, if I go in more details about that discussion, what does it mean? You might remember that when I told you about throughput, latency, and capacity, it was in this context, the fact that we have gigantic capacity that increased by a factor of 200 billion per unit of volume in 70 years, almost 70 years, but the throughput, not so much. So we have a problem. And you see that because of that, we have to accept that we are going to be limited by the throughput, right? This is why we add more machines. But then the latency is even worse, and this is the problem we don't want to have. We don't want latency to make the whole data center idle and waiting for bits to flow around. So we are going to parallelize. This is why we have data centers. This is why we have hundreds and thousands of machines in the data center. The bytes are going to flow in parallel across the machines, right? So then we can read many more bytes at the same time with 100 machines than you can read with a single machine. And this, between throughput and latency, is going to be solved with so-called batch processing. In fact, you didn't know it, but I already told you what batch processing is without saying the words. In fact, when I showed you this is batch processing. It's the idea that we don't want to read small parts of files many times, because then latency would be an issue. Every time you look at a bit randomly in a file, you have to wait to get the bits. However, if instead of random access, you scan the file, when is there latency? Well, there is latency right there at the very beginning. You request to open the file and start scanning it. This is where the latency happens. But once you have begun scanning the file, there is no latency anymore. The bits are just flowing, right? So I repeat that if you do random access here, 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 every time you have to wait. If you scan the file, you only have to wait for latency at the beginning, then it just flows. This is the idea of batch processing. Batches means we process the data in batches at the scale, for example, of files or blocks, as we will see, entire files, entire blocks at the same time. And we do not have this random access of small parts everywhere. This is called batch processing. But parallelism and batch processing are so important that I'm going to actually annoy you with that every single week of the semester. So don't worry, I'll keep repeating and repeating and repeating again parallelization and batch processing, right? So hopefully you will develop an intuition of all of that. Okay. For whom does that make sense, this idea? We are scanning file. We don't want latency to be the issue. We want throughput to limit us. Yes, raise hands? Following? Okay, very good. Okay, now, what is Hadoop? Well, Hadoop is the open source version of all these technologies that were invented at Google. So we are not going to cover the Google file system. We will cover the Hadoop distributed file system. It's the same thing, but open source. So the original works are Google file system in 2003, MapReduce in 2004, and Bigtable, which we will cover in a few weeks, in 2006. And Hadoop took these and put them open source. So the GFS in Hadoop is called the Hadoop Distributed File System, HDFS. MapReduce, they didn't change the name, but it's commonly called Hadoop MapReduce to distinguish it from the original MapReduce. And white column stores, so the Bigtable is called HBase in Hadoop, H for Hadoop, of course. So HBase is the implementation in open source of Bigtables, right? We'll actually look at all three in this course, but today we only look at the distributed file system. MapReduce we'll do in a few weeks, HBase we'll do in a few weeks as well, right? So we keep them for later. Okay. This is a history now, it's even almost archaeology because this is starting to get old, but these are the numbers reported by Yahoo. So Yahoo was actually the employer of Doug Cutting, who is the Hadoop founder, and so this Hadoop was developed there. And so they documented year after year the size of their clusters. This is a number of computers. This is a number of nodes. So it means that in April 2006, they had a data center and they had 188 nodes connected implementing HDFS. Then you see later 300, the same year 600, 1 year later 1,000, 2008 10,000, and then it goes all the way. And here I put a question mark because we don't really know if any company actually reached the 100,000 nodes. I told you, do you remember the limiting factor for the reason why we have difficulty getting past these 100,000? Yes? Yes, exactly. It has to do with energy and cooling. Yeah, so it's a physical limit of the real world that this is very hard to go past that limit. So then you just open other data centers rather than making a data center bigger, right? So exactly. And so you see the largest that is assumed, but this is unconfirmed, was 600 petabytes as of 2016. All right. Okay, but the last confirmed number is 42,000. And that was already 12 years ago, right? 42,000 nodes. These are these machines that we pile up in the racks. Okay. So what's going to happen now? I'm going to follow an approach that I already took for cloud storage and that I will also follow in the rest of the semester, or at least I try to follow this approach, is that I'm going to teach every technology in 2 steps. First, the logical level, then the physical level. What do I mean with that? It's the data independence thing. The logical model means the model, the abstraction of the system, how the user views the system from outside the system, right? So the API and how this is all exposed. This is the logical model. And then in a second step, we will look at the actual implementation, the physical implementation, so what there is inside and how this is actually implemented. I'm doing that first because it's easier to do it that way for you to learn, because usually the logical model is much simpler than the implementation. But second, for pedagogical reasons, because I want to keep saying data independence, data independence, data independence, is this idea that when you are a computer scientist or a software engineer, you want to have a very clean abstraction and you want to shield your users from the complexity. So to the outside users, we give them a very simple model and the documentation and so on, and the users don't even see what's inside. So I don't know who did the PostgreSQL exercises. I'll try it. Okay, some of you. You probably noticed that you didn't even have access or knew what there is going on inside of PostgreSQL. It's like a black box, right? You don't know, and you don't need to know, because all you need to know is that there are relational tables and you can query them with SQL. That's all you need to know. This is the logical model. What's inside is actually directories and files on the hard drives that you don't actually see, and all these query plans and so on that's going on, but you don't actually care. All you care about is seeing your tables in your Jupyter notebook. That's the logical model. So I'll do the same thing for distributed file system. I'll tell you about the logical model, and only after that will I tell you about the actual implementation of HDFS, right? Okay, who is ready for it? Okay, let's go then. So here's the thing, and I'm talking about the logical model. What you have on the left here is the previous unit on cloud storage and S3 and Azure Blob Storage. It's what we call the key value model. So we have bucket IDs and object IDs, and when you have a bucket ID and an object ID, that's a key, then you associate it with the actual content. So these are the little file-like, so the rectangles there. This is an image, this is a video, this is a part of a data set, and so on. So it's a flat key value model. And I told you that even though you can have slashes in the names, this is all fake and virtual. There are no actual directories in there, right? It's only emulated by the interface if you want to view the objects. But in HDFS and in the Google file system, we actually do have, as part of the logical model, the concept of directory or folders, depending on how you call them. You have directories, so you have a tree structure of directories, and then the leaves are files. So the leaves are those that don't have any children anymore. So these are the files. There are 3 files in there, and the blue ones here are directories, right? Okay, and these little triangles, I just wanted to basically emulate how it's shown in your phone or in your computer. When you open the directories, you click in there, and then it closes or opens. And then when it opens, then it shows what there is inside, right? So this is just my attempt to draw something, but I'm awful at drawing stuff. But this is the idea, right? So you have these directories and these files in there. So in HDFS, we do have a file hierarchy as part of the logical model. So the users know about that they have directories and files. Second, the other difference. On the left, once again, this is object storage. This is a black box. You upload objects to S3 or to Azure Blob Storage, and you get them back, right? That's a black box mechanism. Of course, I told you that in S3, if the object is too big, you have the option to upload it in several parts, right? But this is just an API detail. It's a convenience for you to be able to upload it in smaller parts. But in the end, it's going to be a single object, a black box, right? So this is object storage on the left. In HDFS, we have blocks, meaning that the user knows that a file is organized as blocks. In that case, there are 8 blocks, right? This is a file. So you see the difference. On the left, it's a single object. On the right, you see that this object is actually divided in blocks. For whom is that clear? Okay, so this is called block storage. You might have noticed that for the key value model or cloud storage, I use the word object. I try to resist the temptation to call them files. I should say object in the case of S3 or blob storage. But on the right, in the case of HDFS, I can call them files because this is an explicit file hierarchy. So then I will say file and not object. So this is why here I'm saying that the object is in a single big chunk, while on the right, I'm saying that the files are divided in blocks, right? So now, a bit of word of warning. This is again, if you're Swiss, you're used in Swiss German that there are many, depending on where you are, in Basel, in Bern, Schweizerdeutsch, and so on. So we can say in many different ways, it's the same thing here. So depending on who you're talking with and what technology you're looking at, people call things the same thing in different ways. So just be aware that basically block, chunk, split, shard, partition, part, this all means the same thing. It all means that you're basically dividing large things into smaller things, right? So this is the idea. And of course, the people don't use the same word. So in GFS, they call these things chunks, not blocks. But in HDFS, they call them blocks. It doesn't really matter what you call them. What's important is that you understand what's going on. And what's important is that you have the flexibility, if you change the technology, that the word might change, but they still mean the same thing. Okay, so we will see that split is the MapReduce way of calling them. Shard is what we use when we have a directory with plenty of files to store a single data set. Then we call them shards. Partition is also quite popular. In what context would that be? Well, for example, on a hard drive, we say that you can partition your hard drive. It's the same idea of cutting it into several parts, right? Maybe partition is more neutral. It's almost a mathematical term, right? You know, a mathematical partition is basically when you have a set and you have multiple subsets that do not overlap. And when you do the union, you get the whole set. This is called the mathematical partition. Do we have mathematicians? That's true, right? I got it right. Okay, so this is a partition, and it's exactly the same idea as block, chunk, split, shard, and so on. Okay, so if I summarize these two things that I told you, the model of HDFS is extremely simple. We have a hierarchy of files and directories, and each file is logically a list of blocks, right? An ordered list of blocks, of course, you don't want to lose the order. So this is it. If you just want to take a snapshot with your brain of what HDFS is, this is the logical model. Okay? It's that simple. Hierarchy of files and directories, and the files are made of sequences of blocks. Okay. So now, why blocks? Well, first, because that's how we reach the petabytes size, because the blocks have to fit on a single machine, right? But the total size of the blocks together can exceed a machine because you can put different blocks on different machines, right? So this is the secret, having blocks. This is what helps us to go beyond what a single machine can do. And second, it's a quite simple level of abstraction. In fact, it's the same level of abstraction that you have on your hard drive on your computer. The data on your hard drive is actually accessed in blocks too. These are 4 kilobyte blocks. All right. So now when you have the blocks, so now these are all the blocks of all the files. We will see that they are stored together like that. So here, just looking at that, we don't really know what block belongs to what file, but we don't care, it's somewhere else. But basically on the left, you would have like all of the blocks, but you see that it's very easy to just partition it. There you go again, partition. So you can partition that very easily, all these blocks. And this is one machine, this is one machine, this is one machine, this is one machine. So you see, we can spread all of these blocks very easily across machines. Super easy to do. We don't really care what is on what machine, we just spread them. We'll see later that there's still strategies for deciding with the machines, but this is the idea, right? So this is one more benefit of the blocks, is that it's extremely easy to spread them across all the machines in your data center. If a machine becomes too full, you just move over the blocks somewhere else to a machine that has more space, right? It's that easy. Now I have a question for you, which is, what do you think would be the right block size for HDFS? What do you think? So I'm telling you on the left, this is what you have on your laptop. So on your laptop, when you write files with random access, this is done 4 kilobytes at a time. Roughly, it's the order of magnitude. In a relational database, maybe this goes all the way to 32 kilobytes when you read from the hard drive. Like this is what PostgreSQL would be doing. But what do you think about HDFS? Let me ask you for your opinion. Oh, no, that's not the one. That's the one I want to ask. So what do you think? What should be the size of an HDFS block? Should it be 32 kilobytes like a relational database on your local file system? Should it be 128 megabytes, which is a good compromise between latency and throughput? Should it be 2 terabytes because it fits on a local drive? Or should it be 512 petabytes because this is a big data system? You see, we have a majority. We do have a majority. Is the majority correct? See some more answers coming in. Yes, the majority is correct. It is indeed 128 megabytes. Let me come back to explain this. Should be this one. Okay, this is it. I need to tell you why. So first, we can eliminate the obvious. 512 petabytes doesn't work because it doesn't fit on a machine. I say that a block has to fit on a machine. So it leaves us with the other 3. Then let's eliminate the 32 kilobyte answer. Why do we eliminate it? Well, this has to do with what I told you about batch processing and the fact that we don't want to be latency blocked by latency. Let's do a quick calculation. Imagine that you're looking at a data set of 32 petabytes. As an example, 32 petabytes, that's quite reasonable. It fits in a data center. It's roughly the size of a storage stamp in blob storage. So imagine now that you have a data set of 32 petabytes and the blocks are 32 kilobytes. How many blocks are there in the data set? How many zeros? So let's count together. Kilobytes. Okay, so let's start. Megabytes, that would be 1,000 blocks, 32 megabytes. 1,000,000 blocks, that would be 32 gigabytes. 1 billion blocks, that would be 32 terabytes, right? 1 trillion blocks would be 32 petabytes. So if we take a block size in HDFS of 32 kilobytes, we are looking at 1 trillion blocks for a single file. Now, let me give you additional inputs. The latency to access a block is roughly 1 second. 1 trillion blocks, every time you need 1 second. Now, an additional piece of information, 1 billion seconds is how many years? Do you know that? 1 billion seconds? It's 30 years, 31 years. So you can now celebrate when you, some of you, when you will be 31, you can celebrate your billionth second, but this is 30 years for 1 billion seconds. Now 1 trillion seconds, we are looking at 30,000 years. If you read that sequentially, the whole file, block by block, 32 kilobytes, you need 30,000 years to do it. Now you can say, okay, we are in a data center, we do that in parallel, right? So, okay, we have 1,000 machines, so then it's going to take 30 years to read the whole data set. But still 30 years, there's no way that works. You cannot wait for 30 years to query a data set. For whom does that make sense? So we cannot use 32 kilobytes. It doesn't work. We are going to spend the whole time waiting for latency. So this is why we have 128 megabytes or 2 terabytes left. Why not 2 terabytes? Well, 2 terabytes would be too big. First, you could only store a number of blocks on each machine that you can count on your hands, basically 1, 2, 3 blocks per machine. This is not good. First, because I don't know if you've already tried to transfer 1 terabyte of data in a single time over the network, but it's very likely this is going to break or you're going to be interrupted. You probably already experience it when you try to update your operating system. It's usually a few gigabytes that you need to download. That takes actually quite some time, and it might even fail, and you need to do it again. So 2 terabytes is not realistic for this reason, because that's going to cause too many issues. And the other aspect is that you really want hundreds or thousands of blocks on every machine, because you can better spread them and distribute them over the cluster. So this is why we have this sweet spot of 128 megabytes. Some systems use 64 megabytes. You can actually adjust it as a user. This is an option you can change. You just need to be aware that this tends to be increasing. I think Azure now has moved over to 1 gigabyte or 4 gigabytes per block. So this is slowly increasing as the sources get improve over time, but it's the same order of magnitude, right? Less than 10 roughly 10 of difference is not a big deal. 1,000 times more would be a big deal, but 10 is roughly the same order of magnitude. Okay. As an exercise, you can actually try to install HDFS and change the default block to 38 kilobytes, and then you will see how unusable it is basically to try to use it. Okay. A few minutes left, so maybe just a few slides quickly. Then we'll continue next week. In a data center, we have thousands of computers, so obviously they are connected together. But then you need to decide how they are connected together. There are many ways that you can connect the machines together. One of the ways is called peer-to-peer. Peer-to-peer architecture, meaning that every computer talks to anybody. The whole internet and the web is actually that kind of architecture, right? Blockchain as well works like that. As opposed to a centralized architecture, where you have a node that's called the coordinator, for example, and then we have the workers that connect to it, but you have many other synonyms. So if you see them in literature, then you will see that they mean the same thing. So I just call them coordinator and workers, right? Or primary and secondary. And in HDFS, this is how it's organized. One of the nodes, so again, a node is a machine in the cluster. One of the nodes is central, the primary node. It's called the name node, right? The worker nodes or secondary nodes, they are called the data nodes. As you can see here, because I drew them, this is where the blocks are. The blocks are on the data nodes. They are not, there is no blocks in there. There are no blocks on the name node. So again, I repeat, there is only one name node that coordinates everything. And then there's all the data nodes that contain the blocks. Next week, I will give you more details about that, how this all works, how the blocks are stored, how they communicate with each other, what happens when you connect to HDFS and upload a file or read a file and so on. One thing that you must know is that it's slower than on your laptop. So you should try it in exercises if you want, but if you actually connect to a data center on HDFS, every time you type something on the command line is similar to your laptop. It takes every time 1 or 2 seconds to get a response. On your laptop, it's much faster than that when you do ls, for example, to list the files of a directory. So this is much slower, but again, we don't care. What we want to do is process large amounts of data and be throughput bound. Okay, so let's end here. I'm keeping the animation here for next week. So please read the chapter on HDFS. It complements to what I'm doing here. And I want to check that you're following. So it tells me if I was too fast, too slow. And again, you should read the textbook, because if you didn't understand something, then you will find it in the textbook, and you can ask also offline for more explanations. Don't have anybody who understood everything yet. So this still looks good. Again, my goal is to have a majority above 80%. I see that it's, trend. Oh, somebody understood everything. Very good. So that tells me that the rhythm is about right. I should just be careful to not accelerate too much, right? So please do the exercises. So the SQL exercises, it will be useful for in a few weeks. Please read the textbook, quietly, in calm and so on. Just read it again. This is just a repetition of what I'm telling you here. And next week, if you have any questions, I'll answer them, and then we'll take it from there, showing you the inside of HDFS. All right. So thank you very much for your attention, and I will see you next week for the continuation. Goodbye.